I believe that there's one more thing that I wanted to go over in class that we didn't get to before I left. So I've provided this short video for you here. By the way, I wanted to tell you that I'm in Atlanta, Georgia for this week at this Eco Districts conference. My interest is in learning how to do a kind of a community design for sustainable communities. So I hope to bring back some learning for all of us and the future. Here's a combustion problem that involves combusting methane with 20% excess air, and it's asking for the needed airflow rate in moles per hour. Now, it does tell you that methane feed rate is 1 cubic meter at 1 atmosphere and 25 degrees C. Now, we don't know what the dry air conditions are, but we can start with presuming that it's the same set of conditions, 1 atmosphere and 25 degrees C. So in order to do this, we need to know a couple things. One is, what does dry air consist of? And secondly, what does the complete combustion equation look like? Well, in general, there's a convention for working with dry air, and that is that dry air consists of nitrogen gas and oxygen gas, and the ratio is 3.76 moles of nitrogen to 1 mole of oxygen. So dry air, we say that it has nothing. We don't actually account for the argon and the CO2 that's also in air. These are just the generic numbers we use. Another way of expressing that is 79% nitrogen and 21% oxygen. And we'll just, in this class, we'll use this as a convention for dry air. So the stoichiometric equation is here, and I have confidence that you can balance this. Here's our dry air convention. And we start out with an equation that looks like this, just to kind of keep in mind what the reaction is. Now, the thing is, we have 20% excess air. Now, the thing we need to know is that not only do we have oxygen in the air, but we have nitrogen. So what would that look like in an equation? Okay, here's my actual equation. And notice that what I've done here is I've replaced O2 with a coefficient that I don't know, A, times O2 plus 3.76 N2. So we know we have some unknown amount A, but we also know that the ratio of O2 to N2 is this fixed number, 1 to 3.76. And then my product is CO2, 2H2O, then this excess oxygen that's left over, and then the original amount of nitrogen. Remember, nitrogen is a tie component, so this A times 3.76 is going to end up all here in the effluent because nothing happens to the nitrogen. Now I need to think about the basis, and I believe that was in the original question here. We have 1 cubic meter at 1 atmosphere, 25 degrees C, that is being added to this reactor here. So what is then, whoops, I guess I lost the reactor. So here it is, and we're trying to find out the needed airflow rate. So we need to know what this is under these conditions. Well, in order to get these moles in moles per hour, we need to convert this volume to molar rate. So let's go ahead and do that using the ideal gas equation. So we know that pressure times volume is equal to, I'll try that again, pressure times volume is equal to nRT, and if we take the derivative of this, we're going to get that I'm going to go to the next page. P dV dt is equal to dN dt times RT. So the gas constant and the temperature are not changing, nor is the pressure changing, but we've got this sort of volumetric flow rate, and we know that's related to the number of the molar flow rate. So rearranging this gives us the equation that we need to solve. We see that dNdt equals P dV dt over RT, remembering that these values must be in absolute measurements. Let's go ahead and plug those in. So plugging in these numbers for the pressure, the volumetric flow rate, the gas constant, and temperature, and then taking care of the units, what I ended up getting is 40.9 moles per hour of CH4. So you see here that we had 40.9 moles of CH4 per hour flowing in. We know that from the stoichiometric equation that each 1 mole of CH4 requires 2 of oxygen. So 1 mole requires 2 of oxygen. And we know that for every mole of oxygen, we have 1.2 moles of O2 input into our process, because we know that this accounts for the 20% excess. So in doing this math, let's see, I've counted for the CH4 here. Moles of oxygen is the mole of oxygen input. So what we get here, I've got that this gives us 98.1, actually 98.2 moles of O2 input. So we were asking about that. Now, what does that do for our equation? So we can see that this is the amount that was put in here. So the A value is this 98.2. Now we know that we don't use all of it, and we want to, I think our initial question was how much air. So this is the answer. We have 98.2 moles of oxygen, but that's not moles of air. We have to account for the nitrogen as well. Let's do that. So what I get when I do that math is 476 moles of air per hour that's input to the combustion reactor.